So let's talk about rotational work energy and momentum. Now it is very important for us to understand rotational motion, because what we're going to be doing here, we're going just to be adding up on rotational motion, which is circular motion. Okay, so let's begin our discussion with rotational work. Now we know that work is force times distance, that is under work energy and power. Now let's assume to say an object is moving around the circle. So here is my object. Okay, now I'm trying now to push this using the force, which I'm going to call F. So the distance which is going to cover from this point all the way down here, I'm going to call S, which is the arc length in this case. Then we understand to say we're going to have the radius, which we're going to call R. Now there is a concept which I'm going to introduce here, which is torque. But we are going to talk more about torque under static equilibrium. But for now, what you have to know is that torque is given by force times the radius. So we can say it is the distance. In this case, that's the distance which we have. So it is the force times the perpendicular distance. So this is not T, but it's just the symbol which we use for torque. So the force times the perpendicular distance, in this case the perpendicular distance is the radius. Okay, now another thing which you have to remember is that if I've got an object, then this is going to start moving from this point all the way to this point. Let's call this point A, this point B. So this is going to be theta. Okay, so let's say you're moving from point A all the way to point B. The distance which you're going to cover is the S. In this case is the arc length. And we know that this is our radius. Okay, then we can find the arc length to say the arc length is the theta times the radius. Now what we need to know is that the work which we're talking about here is basically the force times the arc length, which is the S. Now the S which we have here is the same as the S which we're talking about there. Therefore I can replace S with theta times R. So I'll say my work will be equal to the force times theta times R. But we know to say torque is given by force times the radius. Now I can isolate this and say I have got Fr times theta. And I know that F times R is the torque. Therefore, under rotational work, work is given by the torque times the theta. So this is the formula for work. Okay, so for now this is what we need to know under work. So work is given by torque times theta, that is under rotational work. Now if we go back to translational work, where we say force or work is given by force times the distance. So in this case the distance is the same as the S. So now the S, when we talk about rotational work, it is the arc length. Now let's go ahead and talk about power. Okay, so in this case we're going to be talking about rotational power. So all the formulas, they are coming from translational power. So we know that power is given by the work times the time. And we also know that work is force times distance. So we can replace work with force times distance divided by time. What else can we see? We can clearly see that power will be equal to the force. I can isolate this, and I do know that velocity is the distance over time. I can replace this with v. Power is the force times the velocity. This formula is under translational power. Now I'll start from there. When an object is moving around the circle, there is radius. This object is moving around the circle. We expect to have angular velocity. Therefore, we know that linear velocity is given by angular velocity times radius. I can replace v with wr. So power will be equal to the force times this. At the same time, we know that we can rearrange this and put it like this, because I know that force times r is the torque. So power under rotational work energy and momentum is given by torque times angular velocity. So let me just put these formulas here. Let me just put this formula here. We have come up with work to be equal to the torque times theta. Then power we are saying is torque times angular acceleration. Now let's talk about energy. Whenever we're talking about energy, we have potential energy and kinetic energy. But in this case, potential energy will not change. It will be the same. Under translational, under rotational, we have mgh. But when we go to kinetic energy, we can notice to say we're going to have something there. So we have got what we call translational kinetic energy, which we know already is given by half mass times v squared. Okay. Then there's also what we call rotational kinetic energy. Now everything starts from here. I can derive the formula which is going to help me to find the rotational kinetic energy starting from translational kinetic energy. As we can see, we have come up with the formula for work using translational work. Then we have come up with the formula for power using translational power. At the same time, we can come up with the formula for rotational kinetic energy using translational kinetic energy. So let's go. What we have to remember, although I'm going to explain about this, but we should know that inertia is given by mr squared. This formula is for inertia. Okay, the general formula for inertia, but I'm going to explain about inertia. I think that is going to be in the next video. Now, what we need to know here is that V is WR. I can replace V with WR so that I now move from translational kinetic energy to rotational kinetic energy. So I'll say rotational kinetic energy will be half the mass times V squared. So now V, I can replace V with MR. So it's going to be MR squared. Or it's going to be MR, but I have to square this. Okay. What else can we see? Now we can see that these two guys, rotational kinetic energy is going to be half. I can clearly see that let's reverse this. We are saying that we need to replace V with WR. So it's supposed to be WR I squared. So now this is going to be the mass W squared R squared. Okay. Now from here I can clearly see that what I'm going to have is going to be rotational kinetic energy will be half. Okay. Then I've got mass times R. I can clearly see that I've got mass times R squared, that is going to be inertia. Then I have this. So this is my formula for rotational kinetic energy. So rotational kinetic energy, it can be represented by RKE or kinetic energy, then I put R here, which is the same. So now we have got three important formulas which we have to take note. We have rotational kinetic energy, which is half inertia times angular velocity squared. That is the formula for rotational kinetic energy. Okay. Now let's see the relationship which is going to be there between work and kinetic energy. Remember we said that under translational work energy and power, we mentioned to say the work done by a particular force is equal to the change in kinetic energy. Okay, so if we can remember very well, we said the work done, maybe let's say the work net, is equal to the change in kinetic energy. Now in this case we are talking about translational kinetic energy. Okay, so the work net will be equal to the change in kinetic energy is the kinetic energy final minus the kinetic energy initial. Okay, so now this is going to be the work net is going to be half the mass V final squared minus half the mass V initial squared. This is the formula for work net under translational work energy and power. Now we are trying to see the relationship which is going to be there between the work net and translational and rotational kinetic energy. So what I'm going to have is going to be the same network, which is going to be, now here we're going to be talking about the change in rotational kinetic energy. Okay, and we know that rotational kinetic energy, we can have the final rotational kinetic energy minus the initial rotational kinetic energy, as simple as that. Okay, so we need to know this relationship is very, very important, and it's going to help us to come up with some different formulas. So this formula is important. So we can use work net to say it is the change in kinetic energy. In a case where we have got only one force, then it's going to be that particular force is equal to change in rotational kinetic energy. Okay. So now what I'm going to do is I'm going to derive the formula for inertia, or another formula which we have to come up with is the formula for torque. So we have two formulas for torque which we have to be familiar with. Now I'm going to do it from here. Initially we said torque is given by the force times the perpendicular distance. In that case, if you have got a circle, it is the radius. Now let's talk more about work. We are saying that work, it can be given as the change in rotational kinetic energy. Now we are assuming to say there is no friction. The only work done by that force is going to be the force applied at that point. So what we're going to have is going to be the work will be equal to the rotational kinetic energy final minus initial rotational kinetic energy. So work will be equal to half. We know that this is going to give us inertia, this final squared minus half inertia initial. Now I can clearly see that I can factor out half inertia. So I'm going to have inside there, I'll have the final minus the initial. Now I know that work is torque times the theta. So I'll replace work with torque times the theta is going to be equal to half inertia, the final squared minus initial. Now it is squared. Now let's get rid of this. Now I can replace final angular velocity minus initial angular velocity with something else. Let's see. I can clearly see that this is coming from this formula. It is the final angular velocity is equal to the initial squared plus 2 angular acceleration times theta. Now I'll shift the initial to the other side, then I'm going to have the final squared minus initial squared will be equal to 2 alpha theta. So I'm going to replace where there is this with 2 alpha theta. So torque times theta will be equal to half inertia. Then here I'm going to replace with 2 alpha theta. I can clearly see that 2 and 2 can go. Then I'll remain with torque times theta is equal to inertia times this. I can also see that theta appears both sides. I can cancel it. Therefore, another formula for torque is inertia times angular acceleration. So we need to be familiar with these two formulas. They are very, very important. So these are the two formulas for torque. So torque is given by force times perpendicular distance. I can also find torque using inertia times the angular acceleration. That is also important. Okay. So this is it for the introduction of rotational work, energy, and momentum.
Are you enjoying this video lesson? So you can actually access the entire topic you are watching or the entire practice questions of a video that you may be watching right now. So if you go to our website is transcendedinstitute.net. Okay, so there are 3 ways that you can access our videos. So you can use Patreon, you can use channel memberships. If you're in a country where it's allowed, you'll be able to access our full topic videos and full practice questions. So alternatively, you can access the videos using our learning portal. The link is learn.transcendedinstitute.net. So I'll show you a few videos that you can have access to after registering. So for example, if you had to open mathematics as at now, these topics are the ones that are available, which you can learn from scratch. I can just give you an idea of, so you learn everything from scratch, meaning that even if you're learning something for the first time, these videos are there to help you with concepts as well as practice questions. So for example, these are tutorial sheet solutions from different tutorial sheets, which can help you as well get to learn faster and remember. So binomial as well, there it is. And of course, this applies to all these other topics that are available. Trigonometry as well, calculus, depending on the topic that you're interested in mathematics. So you can just head over to the site at now to check what is currently available. Even without registering, you should be able to see the content in each topic. So let's assume you're interested in physics. These are the topics available as at now. So if you open chemistry, these are the topics available as at now: electrochemistry, stoichiometry, thermochemistry, kinetics, equilibrium, solubility, equilibrium, atomic structure. So trust me, if you open these videos, you might have learned the topic in full. Let me show you stoichiometry. So stoichiometry, we have all the way up to 21 videos, including the tutorial sheet solutions, which will help you to practice both the concepts and also prepare for questions. Okay, so feel free to head over to the site and check out these videos on your own. So equally, biology videos are also available, which you can also basically get to access. So these are the topics available so far. Yeah, so pretty much these are the ways you can easily access our full membership videos that you don't have access to on the channel.
So let's talk about rotational inertia. So what is inertia? Inertia is basically the tendency of the body to resist its motion. So inertia depends on mass. What is happening there is that if you have got an object which is here, okay, let's say this object has got the mass of 2 kgs. Then you have another object, or in this case, let me just use anyway, let me use the same thing. I'll have another object, then this object will have 10 kgs. So the inertia gets bigger as the mass gets bigger. So the basic idea behind inertia is that inertia is given by the mass times the radius. Okay, so let's assume to say the radius of this is the same. Let's say the radius here is 3 meters, then here is also 3 meters, meaning that inertia for the first object is going to be 2 times 3, which is 6. Now since there is mass times r, we can see that mass is in kgs, then radius is in meter, but since it is, or is supposed to be mass times r squared, that is the formula for inertia, that is the general formula. So it's going to be meter squared. Then here is going to be inertia is equal to 10 times 3, which is going to be 30. So as we can see, the object with bigger mass tend to have greater inertia. So what we can conclude there is that inertia depends on mass. So inertia is direct proportion to mass. As the mass gets bigger, inertia will also go up. So what are we saying? We are saying that if the mass goes up, inertia goes up as well. If the mass goes down, inertia will go down. Now, we are saying that it is the tendency of the body to resist its motion. Let's assume to say you are moving in a car, then the car, or let's say you are moving at a very high speed in a car, then the driver applies brakes from nowhere. What you're going to discover is that you are going to go forward, backward, at the same time you go again forward and then backward, then after some time you come back to your original position. So what makes you to go back to the original position is inertia. That is just basically the tendency of the body to resist its motion. Now when we are talking about rotational work and rotational work energy and momentum, we need to be familiar with what inertia is. So now we need to know that inertia can be given by formulas depending on the shape and the size of an object. So in most cases, you are going to be given the formula for inertia. But what you should know is that the general formula for inertia is mr squared. At the same time, what you should know is that if they ask you the inertia of the disk, it is half mr squared. Then inertia of the body, maybe inertia of the person, is given by mr squared. There is no half. Now I'm going to give you about 4 shapes which you need to be familiar with, but it's not even important. Always when they ask you this question, they are going to tell you the formula. They're going to give you actually. So let's say we're talking about a disk. So if you have got a disk, so let's assume that that is our disk. Now this disk, that is the point of axis. So inertia of the disk is always given by half mr squared. Then now let's say you have got a sphere. So if you have got a sphere, like this, not really this, but this. If this is the solid sphere, so inertia of a solid sphere is given by 2 over 5 mr squared. Then there is what we call solid cylinder. I can also give you another solid cylinder. Let's say we have got a cylinder. Okay, so here is my cylinder. So the radius is there. So inertia of the disk and the cylinder is the same. So inertia of the cylinder is going to be mr squared. Now you're going to be given the formulas always. So, but what we need to know is that the inertia of the disk is given by half mr squared. If they ask about the solid sphere is 2 over 5 mr squared. Then the cylinder and the disk is the same. Then if they ask you about the inertia of the solid mass, if you have got an object which is just the mass is just concentrated on one part like this, then inertia in that case is mr squared. So that's why I said the inertia of the person, since the mass is just concentrated on one part, so the inertia of the person is mr squared. Now that we know that inertia is given by mr squared, and we have got different types of shapes and different formulas, let's see how we can solve some questions under the same topic. So I've got my first question here, which is saying a heavy solid metal wheel has a moment of inertia of 2000 or 250 kg meter squared. What is the needed torque to produce an acceleration of 3 rad per second squared? I believe we talked about torque. We said torque is given by Fr. Another formula for torque, we said it is inertia times the angular acceleration. Now in this case, we want to find torque. Okay, and we have been given the inertia. We also have the acceleration, so I can use this formula to find the torque. So meaning that torque will be the inertia is 250 times the acceleration is 3. So torque will be 250 times 3, which is going to be a 750. Now the SI unit for torque is Newton meter. Why are we saying Newton meter? The force here is in Newton, R is in meters. So now even if you derive this formula, you end up having the same units, Newton meter. Okay, now let's have the next question. The question is a 1.5 kg grinding stone of 8 centimeters radius is turning at 130 rad per second. The driving motor is switched off and the axe is pressed tangentially against the grinding stone with a force of 2 Newton. How long will it take, or how long will it the grinding stone to stop? How long will it take the grinding stone to stop? Yeah, that was supposed to be how long will it take for the grinding stone to come to stop. Anyway, so now let's come up with data. I believe data is going to help us to know the formula which we are going to use. So we have got the mass of 1.5 kgs. The radius, it is 8 centimeters. We divide by 100, 0.08 meters. We have our initial velocity, our initial angular velocity to be 130 rad per second. Now it was switched off, meaning that the final was 0. The final angular velocity is 0 rad per second. What else do we know? Now the force was acting against, meaning the force is negative. So I've got the force of 2 is going to be negative 2 Newton because it was acting against. Okay, so the question is one to find time. Generally speaking, here we can only use this formula to find time, I believe so. Because I can see that I have my final velocity, I have my initial velocity, then I don't have the final. I don't have the angular velocity. But I do have the the radius and the mass. I can find the inertia. I can find the angular velocity. What did we say? We said that torque, we start from torque, where we said um, torque is given by the inertia times the angular acceleration. Okay, but we also know that another formula for torque is the force times r. I have the force, I have the r. Therefore, I can replace this with what I have here. Now, I also know that inertia, we're talking about inertia of the disc, grinding stone. Okay, so grinding stone, meaning we're going to be talking about the inertia of the disc. But initially, if they ask you in your test or exam, they're going to give you to say, given that the inertia of the grinding stone is half mr squared. So you don't have to master the formulas of inertia because they're going to give you. But what you need to know is, in case they don't give you, you should know that the grinding stone, the inertia is half mr squared. Then again, the inertia of the disk is half mr squared. The inertia of the person is just mr squared. The inertia of the solid sphere is 2 over 5 mr squared. Now let's go ahead and solve this. So we have got inertia. I'm going to replace inertia with half mr squared times angular acceleration. Why I'm doing this? Because I know the mass, I know the radius, I know the force. I can now find the angular acceleration. But what I'm going to do is I'm going to do times 2 both sides so that I get rid of half. So it's going to be 2 fr is equal to mr squared times this. I'll divide both sides by mr squared. Here mr squared. What I'm trying to do here, I'm trying to make the alpha as a subject of formula. So I'll have 2 fr divided by mr squared. We can clearly see that we have got r on top and r down, so I would remain with 1r. Therefore, my acceleration in this case will be, my angular acceleration will be 2f then divided by mr. Let's plug in the values. Remember, the force was acting against, so it is negative, and we can clearly see that it's making sense because it was turned off, meaning it was decelerating. So we expect to have angular acceleration to be negative because it was decelerating. So it's going to be 2 times negative 2 divided by the mass is 1.5 times the r, which is 0.08. So my angular acceleration will be, on top is negative 4, so negative 4 divided by 1.5 times 0.08. So I'm getting my angular acceleration to be negative 33.33 rad per second squared. Now, in a case where you don't know how to punch this direct, what you can do is you can find this separate and find this separate and then divide it. But if you know, what you can do is you can just say negative 4 divided by, then you open the brackets on your calculator, put 1.5 times 0.08, then close the brackets, the answer, so you get that one. Now we can go ahead and find from the formula From our formula here on top, which is in lead, we have now the angular acceleration. We want to find the time. So we can make t as a subject of formula, whereby we can shift this alpha to the other side. It's going to be like this. I'll divide both sides by alpha, both sides by alpha. T will be equal to the alpha final, alpha initial divided by alpha. This is not alpha, it's omega. So the omega final minus omega initial divided by alpha. Yeah, angular acceleration is alpha and angular velocity is omega. Now I can see that my t will be equal to, the final is 0, the initial is 130 divided by negative 33.33. So using my calculator, I'm finding that the time is 3.9. I'm getting 3.9 seconds to be my time. So it will take about 3.9 seconds. If you can round it off and say it's 4 seconds, it will take about 4 seconds or 3.9 seconds for this grinding stone to come to stop. So this is the basic idea behind inertia. Now let's talk about the relationship between rotational inertia and torque. Remember, we have said that from our previous video, we said that torque can be given by two formulas, and we have derived those two formulas. We said that torque can be given by the force times the perpendicular distance, in this case is the radius. Then again, torque is given by inertia times the angular acceleration. Now this torque and this one is the same, therefore you can set them equal to each other. You can say inertia times angular acceleration is equal to the force times r. Now this is very, very important. Okay, now I have got some questions and the same relationship between rotational inertia and torque. So the first question is this question is from one of the exam past papers. So it's saying a merry-go-round has a mass of 100 kg and radius of 1.6 meters. Consider it as a uniform disk of a moment of inertia of equal to half mr squared. A man pushes with a horizontal force of 80 newton tangentially to the merry-go-round. But one, which is saying, so this question had 10 marks. So what is the angular acceleration produced? But two, starting from rest, how fast will the merry-go-round be moving? That is in revolution per second after 12 seconds. How many revolution, that is part 3, how many revolution would the merry-go-round have made in 12 seconds? So let's start with part A. Part A is asking about the angular acceleration. Now, from the relationship which I've just come up with here, which is the torque is equal to force times r, again torque is given by inertia times the angular acceleration, I can use that to find the angular acceleration. Okay, so from our data we can clearly see that we have the mass to be 100 kg, our radius is 1.6 meters, our inertia we have been told that is half mr squared. What else? The force is 80 newton. So the question is, what is the angular acceleration produced? So I can use this formula to find my angular acceleration. Now what I can do at this point, I know that inertia is given by half mr squared. I can replace this with what I have. So I'll say inertia, I'll replace it with half mr squared times angular acceleration is equal to the force times r. Now, sometimes if you are confused with what I'm doing here, the best way you can do is you can find inertia alone separately using that formula, and then you just plug in direct. That is just okay. So what I'm doing here is I'm just replacing where there is inertia with a half mr squared. But it's okay. You can find the inertia, plug in the mass, the radius, then square it. That is going to be the inertia. Plug in the inertia there, divide both sides by inertia. That is going to be your angular acceleration. Okay? So you should try that. Then you're going to see that the answer is going to be the same. Now, for me to get rid of the half, I can divide, or I can do times 2 everywhere. So 2 and half is going to be cancelled. I have m r squared alpha is equal to f. I have 2 fr. But I can also see that I can divide both sides by m r squared, even here by m r squared. So these two can cancel. Then here again, this and 1r will cancel, I will remain with 1r. So alpha will be equal to 2f divided by mr. Let's try to plug in the values. Our alpha will be 2 times 80 divided by, the mass is 100 times the radius is 1.6. So we expect our angular acceleration to be 2 times 80 is 160. I'll put 160 here. I divide everything by 100 times 1.6 is also 160. Okay, so now if I divide 160 divided by 160, I'll get 1 rad per second squared. So that is my angular acceleration. Now part B is asking us, now I can get rid of this. Okay, part B is asking us to find, is saying starting from rest, meaning that the angular acceleration in that case, because it is starting from rest, is 0 rad per second. Starting from rest, how fast will the merry-go-round be moving in revolution per second after 12 seconds? And we have been told that the time now is 12 seconds. Using those three formulas, we have the first formula which we have to know, the final angular velocity is equal to the initial angular velocity plus angular acceleration times time. Another formula which we need to know is that the theta is equal to the omega initial times time. Okay, then plus, okay, plus half angular acceleration times t squared. Another one is the omega final squared is equal to omega initial squared plus 2 alpha theta. Now, using these formulas from the data which we have, which formula is going to help us to find the final angular velocity? I believe the first formula can work. I can't use the second formula because there is no final angular velocity, so I can't use this. I can use this, but I don't have the theta in this case, so I can't use that. The only formula I can use is the first formula. Okay, now the first formula is this is equal to that. I'll shift initial to the other side. I'll have the final minus initial is equal to alpha t. Let's divide both side by t, both side by oh, we are trying to find the final. Sorry, we are trying to find the final, and we have the time. Let's just plug in dialect. So the final will be, the initial is 0, this has to be plus, so plus acceleration is 1 times the time is 12, so the final will be 12 large per second. But the question is, we need to leave the answer in revolution per second, so we have to convert this from large to revolution per second. What we should know is that in one revolution there is 360 degrees. At the same time, there is 2 pi lad, so I can use this to convert whatever I want to convert. Now I have 12 lads. I'll set the units in such a way that they should cancel each other, so I'll say in 2 pi lad there is 1 revolution, because we're saying that 1 revolution there is 2 pi lad. At this point we can see that lad and lad can cancel. Now I'll have 12 divided by 2 pi, so 12 divided by 2 pi, which is giving me 1.91. So my angular final will be 1.9098. I'm just rounding off to say 1.91 revolution per second. Now because seconds is seconds, unless if it was unless if we were told to say we need to find the answer in revolution per second. Now using dimension analysis, the best way you can do is this. You say in 2, you have got 12 lad per second, so you say in 1 revolution is equal to 2 pi lad, which is the same, so second you put them down there. Okay, so that is it for question 2. Let's now go to part 3, which is saying, let's just put the final here. The final is in lad is 12. Okay, then they want us to find the revolution anyway. Now I can get rid of this. So how many revolutions would the merry-go-round have made in 12 seconds? Okay, whenever you see a question which is asking about revolution, just know that they're asking about the theta. Always, if they're asking about revolution, they're asking about the theta, meaning that I can use the second equation because I have the time, I have the angular acceleration. I can also use the final, or the third equation, because I have the final and I have the initial. Okay, so let me use this one, but you can also use this one. You'll be able to find the same answer. So I'll use the final initial squared plus 2 alpha theta. Let's shift this initial to the other side. It will be minus initial squared is equal to 2 alpha theta. We want to find theta, we divide both sides by 2 alpha, even here by 2 alpha. So we can see that this will cancel, so our theta will be equal to final squared initial divided by 2 alpha. Let's plug in the values. So we plug in the values, we're going to have theta to be equal to, I'm going to have the final is now 12. Now I have to square it. Initial is 0. I square it, divided by 2, acceleration is 1. So theta will be equal to 12 squared minus 0 divided by 2 times 1, which is just 2. So it's 72. So this is 72 lad. Okay, 72 lad. Now the question is how many revolutions? So we need to convert this one now to lad. Okay, so converting this to lad, we can clearly see that we're going to have theta to be equal to, let me just do this, I convert it direct, it will be 72 lad times, in one revolution I'll set the unit in such a way that they should cancel each other. There is 2 pi lad and lad will cancel. I'll divide 72 by 2 pi, so I'm getting my theta now in revolution to be 11.459, which is the same as 56 revolution. As simple as that. Now you can also use the second formula to find that, and you can say that you're going to have the initial, the theta to be equal to, you can also use this formula. So theta, the initial is 0, so this one is going to be cancelled because the initial is 0. So have half, then the angular acceleration is 1, the time is 12, we square it. Alpha will be 12 squared is 144, 144 divided by 2 is 72 lad. So you convert this to revolution, you find the same answer. So that is it for this question. But I have another question here, which is also relationship between the inertia and the angular, the rotational inertia. Rotational inertia and what? So we're talking about rotational inertia and torque. Okay, so the relationship which is there, we can see that torque is helping us to come up with the initial formula. So another question is saying a wheel of radius 6 centimeters is mounted so as to rotate about the horizontal axis through its center as shown in the figure below. A string of negligible mass wrapped around in a circumference carries a mass of 200 grams attached to its free end. When allowed to fall, the mass descends through 100 centimeters in 5 seconds. Calculate part A, the angular acceleration of the wheel. Then part B, they are saying we should calculate the moment of inertia of the wheel and the tension in the cord. Now to calculate the tension of the so what I'm going to do here is I have first to come up with a free body diagram. Okay, I can clearly see that it was in free form motion, therefore I can see that the tension is pointing upward, but there is a force which is pointing downward, which is the weight force. In this case is mg. Now it was descending, definitely it was coming to rest, so the acceleration has to be negative because it was decelerating. Okay, now what we should know is that the relationship still starts from here. Torque is given by force, in this case is the tension force. So tension force, I'll say Ft. Okay, so Ft times R is the radius in this case. Okay, now from our data here we can clearly see that we have got the radius which is 6 centimeters. I'll convert it, I divide by 100, I'll get 0.06 meters. What else? I also have the mass. Okay, the mass which is the mass of this. Okay, the question is it carries a mass of 200 grams attached to its free, so this is the guy we're talking about, so I'll put m. Now the mass is 200, I divide by 1000, so 0.2. What else can we see? We have got it descended. Now what we have to remember here is that it started from here, so it's going to descend from this point, okay, from this point all the way to here. Now this object has got the mass, then there is mg here, so it descend the distance from this point all the way to there. It was about 100 centimeters. In that case, I'll just say d, or h, which is the same as h, is 1 meters. So the distance is 1, which is the same as the height in this case. The time is 5 seconds. Now the question is, calculate the acceleration. Okay, now what we should know is that torque is also given by inertia times the angular acceleration. So from the previous question, we said that we can say inertia times angular acceleration is equal to the force times r. Now in this case, we don't have the tension force, then we also don't have the inertia. The question is, we need also to find the inertia. Then again, the question is find the angular acceleration. So what we can do now is this. Let's see the relationship which is going to be there for tension force. I'll say for the tension force, I know that there is a force pointing upward. Okay, that force is the tension force. An object is coming down, the acceleration is definitely negative. The summation of all the forces in y direction, okay, we have got the tension force pointing upward minus mg pointing downward. Now according to Newton's second law, this is going to be replaced by mass times acceleration, but in this case acceleration is negative, so I have to say negative ma is equal to the tension force minus mg. I have to shift this to the left hand side, so it's going to be negative ma plus mg, okay, is equal to the tension force. Now I can write this and say the tension force is equal to, I can start with mg, okay, mg then minus ma. Now I can see that this is the formula I can use to find the tension force, but I don't have the acceleration. But now let's do this again. The question here, but the last question is saying we need to find the tension force. Now I can start with the tension force, then I come to the moment of inertia, okay, and angular acceleration. Once I have the tension, then it's going to be easy. Now I will just start now plugging in the values there, then I find. Okay, so meaning I can first find the last question, I come then to the, if I want I can go now to the second. Now we can't solve this without finding the tension force. That's what I mean. So we need first to find the tension force. So we need first to find the acceleration. We can find the acceleration because it started from rest. We know the initial velocity. Okay, the initial velocity, meaning it was 0. I want to find the acceleration using this formula. D is equal to initial velocity times time plus half acceleration t squared, because it was coming down. The distance is 1, the v initial is 0, the acceleration is the one we're trying to find, the h is 1, or which is the d, the time we've been told is 5. Now let's go ahead and find the acceleration. Now this is going to be cancelled because the initial acceleration velocity is 0, so it will be d is equal to half a t squared. Let's do times 2 everywhere to get rid of half, so it will be 2d is equal to acceleration t squared. We divide both sides by t squared, even here by t squared, so these will cancel. I'll have t, or I want to find acceleration, so I'll have acceleration to be equal to 2d divided by t squared. So acceleration will be 2 times 1 divided by the t is 5, but we square it. So acceleration will be, okay, so the acceleration is going to be 2 times 1, which is just 1. I divide by 5 squared, which is 25. So the acceleration is 0.08. Let me put it here. Acceleration is 0.08 meters per second squared. That is my acceleration. Now, I know now the acceleration. I can go ahead and find the tension force. At the same time, I can go ahead and find part 1, which is the angular acceleration. Now, I can use this. I know that linear acceleration is given by the angular acceleration times r. Linear velocity is given by angular velocity times r. Linear displacement is given by angular displacement times r. These formulas are very, very, very important. Now, in this formula, I can make, I have the linear acceleration. I can make, now I'm trying to solve part A now, which is part 1. Okay. Now I can get rid of this. So I'm going to say A is equal to alpha times r. I can divide both sides by r. These they will cancel. Alpha will be equal to A over r. So A is 0.08. R is 0.06. So my alpha, it will be 0.08 divided by 0.06, which is 1.33 rad per second squared. I'll put it here. So my alpha is it's just 1.333, so I can put it in 3 decimal places. Rad per second squared. Now I'm done with that. Now I can go ahead and find the tension force. That is now part 3. So the Ft is equal to, I can factor out m, g minus l. Ft will be, m is 0.2, g is 9.8 minus 0.08. So my Ft will be equal to 9.8 minus 0.08, that is inside the brackets there, then times 0.2. I'm getting my tension force to be 1.944 newtons. Now, using this formula, I also know that I can find the moment of inertia. Okay? Because I have everything now. Now I want to find the moment of inertia. I'll divide both sides by alpha, here by alpha. So inertia will be equal to the tension force. I have that Ft times r divided by alpha. So I'll have the moment of inertia will be equal to, the tension force is 1.944 times the radius is 0.06. I divide this by the alpha is 1.333. Okay, so moment of inertia will be 1.944 times 0.06. I divide this by 1.333. So I'm getting moment of inertia to be 0.0875. Now inertia is mass times r squared. So mass is kgs, the radius is in meter, but it is now squared, so it is kg meter squared. So this is now kg m squared. So this is my moment of inertia. Now I can see that part A is asking about angular acceleration. So the angular acceleration is this one. Part B is asking about the moment of inertia. So the moment of inertia is this one. Part C is asking about the tension in the cord. The tension in the cord is this one. So this is important. We have to know this. We need to know the relationship which is there between the rotational inertia and the torque. And it's going to help us to solve a lot of questions.
Are you enjoying this video lesson? So you can actually access the entire topic you are watching or the entire practice questions of a video that you may be watching right now. So for example, if you get to check right now, these are 4 videos which shows member only content. So for example, this trigonometric tutorial sheet is like 5 hours 48 minutes. There are other tutorial sheet solutions and other topic videos available fully here. You can see the hours that they are. So on YouTube, the ones that are available for free, just like maybe half of that, or even just a third of the total time. All these tutorial sheets, you have access to them. So this is actually available in all the courses. For example, you can see chemistry as well, stoichiometry 4 hours, atomic structure. So these videos, you can access them in 3 different ways that I'm going to show you. So if you go to our website is transcendedinstitute.net. Okay, so that's our website. So this is what we do. Of course, Transcended Institute, we just make tutorial videos. So depending on your location, there are 3 ways that you can access our videos. So you can use Patreon, you can use channel memberships. If you're in a country where it's allowed, you'll be able to access our full topic videos and full practice questions. Okay, so you can also download our mobile app. The link is here. If you're on Android, I believe by the time you may be watching this video, even the iOS app may also be available. Okay, so alternatively, you can access the videos using our learning portal. The link is learn.transcendedinstitute.net. So I'll show you a few videos that you can have access to after registering. So for example, if you had to open mathematics as at now, these topics are the ones that are available, which you can learn from scratch. I can just give you an idea of, so you like learn everything from scratch, meaning that even if you're learning something for the first time, these videos are there to help you with concepts as well as practice questions. So for example, these are tutorial sheet solutions from different tutorial sheets which can help you as well get to learn faster and remember. So binomial as well, there it is. And of course, this applies to all these other topics that are available. Trigonometry as well, calculus, depending on the topic that you're interested in mathematics. So you can just head over to the site at now to check what is currently available. Even without registering, you should be able to see the content in each topic. So let's assume you're interested in physics. These are the topics available as at now. So you can actually just head to the site to check the topics that are available at the time you're watching the video. So for example, I can show you work. These are videos available explaining work, including the tutorial sheet based on work. Okay, let's say you're interested in circular motion. These are the videos available on circular motion with tutorial sheet solutions. Linear momentum. So if you watch these videos, trust me, you should have understood the topic in full. For example, momentum, this is what you get to learn. Check the length of the videos, and I mean they are. And then I can show you now a bit of some chemistry. So if you open chemistry, these are the topics available as at now: electrochemistry, stoichiometry, thermochemistry, kinetics, equilibrium, solubility, equilibrium, atomic structure. So trust me, if you open these videos, you might have learned the topic in full. Let me show you stoichiometry. So stoichiometry, we have all the way up to 21 videos, including the tutorial sheet solutions, which will help you to practice both the concepts and also prepare for questions. Okay, so feel free to head over to the site and check out these videos on your own. So equally, biology videos are also available, which you can also basically get to access. So these are the topics available so far. Yeah, so pretty much these are the ways you can easily access our full membership videos that you don't have access to on the channel.
So now let's talk about the combination of rotational and translational motion. So I believe um, you know what translational is. Whenever we're talking about translational, we're talking about in this case, it's going to be the conservation of energy actually. So it's rotational and translational. So let's say you have an incline. Okay, that is going to be my first explanation. If I have my incline, so allow me to call this point to be point A, this point to be point B. So let's have a disk here. Now that disk is going to roll down all the way there. So let's have this distance to be L. Let's have this to be H, the height. Let's have theta as the angle of the incline. Now, here we want to talk about the conservation of energy. So what is happening is that we know that whenever we're talking about conservation of energy, we're talking about the potential energy and kinetic energy. Initially, we are talking about the mechanical energy, and we mentioned to say mechanical energy is just basically the sum of all the energy, or the summation of all the energy present at that point. So in this case, we have potential energy plus kinetic energy. Now what we have to remember is that the conservation of energy states that energy cannot be created nor destroyed, but it can be transformed from one state to another, meaning that the initial mechanical energy has to be equal to the final mechanical energy. Okay, now let's forget about rotational. Let's just concentrate on translational. Let's assume to say an object is moving from point A all the way to point B. So we say the mechanical energy at point A will be equal to the mechanical energy at point B. That is, we are talking about translational. Forget about rotation for now, but I'll come back to that. Now, mechanical energy is the sum of the potential energy plus the kinetic energy. So I'm going to say plus the kinetic energy at point A, even here at point A. This has to be the potential energy at point B plus kinetic energy at point B. So initially this is rotational, is a translation. I'll put a T there. Now translational kinetic energy is given by half mv squared. Okay, now when we talk about the combination of rotational and translational motion, when an object is moving, this object is not only moving but it is also rotating. Therefore, when an object is rotating, we expect to have rotational kinetic energy. Okay, meaning that the mechanical energy at point A has to be equal to the mechanical energy at point B. Now if it is rotating while moving, we expect to have the potential energy at point A plus the kinetic energy, which is translational since it is moving, plus the rotational kinetic energy at point A. Now, meaning we have got two types of kinetic energy. When an object is rotating while moving, meaning we have got two types of kinetic energy. We have got translational kinetic energy and rotational kinetic energy. Rotational kinetic energy is given by half inertia times angular velocity squared. So this is going to be equal to the potential energy at point B plus translational energy at point B plus rotational kinetic energy at point B. So this is the general formula for the combination of rotational energy, the combination of rotational and translational energy. Now, what is happening here is if an object starts from rest, meaning that we don't expect to have rotation, we don't have the velocity, so we don't have these two. So it will be the potential energy. Then when it reaches at B, we don't expect to have potential energy because H will be 0. So we're going to have potential energy at point A is equal to the kinetic energy at T, which is the translational kinetic energy plus rotational kinetic energy. Now let me show you where this formula is coming from. It is coming from the translational kinetic energy actually. So if I know that kinetic energy is given by half mv squared. Now when an object is moving, we expect to have angular velocity. Linear velocity is given by angular times the radius. I can replace v with wr, so I'll have kinetic energy will be equal to the mass. V is wr, but it is squared. Kinetic energy will be half mw squared r squared. So we know that mass times radius squared is the inertia. So it will be rotation kinetic energy is given by half inertia times angular velocity. Now I've derived this formula. In general, what we are trying to say here is when an object is moving, it is moving while rotating, or sometimes they're going to say it rolls, meaning it is rotating. Meaning that there are two types of kinetic energy. We have got rotational kinetic energy and translational kinetic energy. Okay? Now, I believe you're going to understand this when we start now solving questions. Now, I've got few questions which you have to work on. The first question is a solid disk start rolling from rest at the top of a slope 12 meters long and reaches the bottom 12 seconds later as shown in the figure below. What is the angle of the slope with respect to horizontal? Use the energy conservation method. So I'm from explaining to say this is the question here is saying it roaring. So it is roaring, meaning there is kinetic energy, which is translational kinetic energy and rotational kinetic energy. So what it means there is that rotational kinetic energy is always there. Now if an object is moving while roaring, then we have got rotational kinetic energy and the translational kinetic energy. So I've got also this question. This question is exactly as the question which we are solving. Now the question is a solid ball starting from rest rolls without slipping down an incline, rolls without slipping down. So if it was slipping, meaning we don't have, if the question says it was slipping, meaning there is no rotational kinetic energy, meaning it was not rolling, it was just slipping, it was just coming from there then down. Now it rose without slipping, okay, meaning it was rotating. So there is rotational kinetic energy. So we need to use the same concept which we have just used from the question which we are from solving. Find the angle and then send me the answer in the description. Okay, now let's solve the different one. We have got this question which is saying a hoop of radius 0.06 meters start from rest and rolls down a slope without slipping. Okay, meaning it was rotating. So if they say without slipping, meaning there is kinetic energy, translational kinetic energy and rotational kinetic energy. If they say slipping, meaning there is no rotational kinetic energy, there is only translational kinetic energy. Part A, which is part 1, find its linear and angular speed when it reaches a point 0.5 meters vertically lower than its starting point. B, find the linear and angular speed in part 1 above, the slope where perfect smooth so that the hoop just slipped and does not roll. So they're saying that it's going now to slip without rolling, meaning there's no rotational kinetic energy. Now let's come up with a free body diagram. So this is going to be our free body diagram, which I'll just have. Here is my free body diagram. Also the last one, which is the most interesting question, which is asking about a disk of moment of inertia 0.1 kg meter squared about its axis and the radius of 0.2 it released from rest and it rolls down as a plane down a plane inclined at 30 degrees to the horizontal. The mass of the disk is 5 kg. Calculate the angular velocity in rad per second after it has rolled 2 meters down the plane. Now here,
Are you enjoying this video lesson? So you can actually access the entire topic you are watching or the entire practice questions of a video that you may be watching right now. So for example, if you get to check right now, these are 4 videos which shows member only content. So for example, this trigonometric tutorial sheet is like 5 hours 48 minutes. There are other tutorial sheet solutions and other topic videos available fully here. You can see the hours that they are. So on YouTube, the ones that are available for free, just like maybe half of that, or even just a third of the total time of these tutorial sheets, you have access to them. So this is actually available in all the courses. For example, you can see chemistry as well, stoichiometry 4 hours, atomic structure. So these videos, you can access them in 3 different ways that I'm going to show you. So if you go to our website is transcendedinstitute.net. Okay, so that's our website. So this is what we do. Of course, Transcended Institute, we just make tutorial videos. So depending on your location, there are 3 ways that you can access our videos. So you can use Patreon, you can use channel memberships. If you're in a country where it's allowed, you'll be able to access our full topic videos and full practice questions. Okay, so you can also download our mobile app. The link is here. If you're on Android, I believe by the time you may be watching this video, even the iOS app may also be available. Okay, so alternatively, you can access the videos using our learning portal. The link is learn.transcendedinstitute.net. So I'll show you a few videos that you can have access to after registering. So for example, if you had to open mathematics as at now, these videos, these topics are the ones that are available, which you can learn from scratch. I can just give you an idea of, so you like learn everything from scratch, meaning that even if you're learning something for the first time, these videos are there to help you with concepts as well as practice questions. So for example, these are tutorial sheet solutions from different tutorial sheets which can help you as well get to learn faster and remember. So binomial as well, there it is. And of course this applies to all these other topics that are available, trigonometry as well, calculus, depending on the topic that you're interested in mathematics. So you can just head over to the site at now to check what is currently available. Even without registering, you should be able to see the content in each topic. So let's assume you're interested in physics. These are the topics available as at now. So you can actually just head to the site to check the topics that are available at the time you're watching the video. So for example, I can show you work. These are videos available explaining work, including the tutorial sheet based on work. Okay, let's say you're interested in circular motion. These are videos available on circular motion with tutorial sheet solutions. Linear momentum. So if you watch these videos, trust me, you should have understood the topic in full. For example, momentum, this is what you get to learn. Check the length of the videos, and I mean they are. And then I can show you now a bit of some chemistry. So if you open chemistry, These are the topics available as at now: electrochemistry, stoichiometry, thermochemistry, kinetics, equilibrium, solubility, equilibrium, atomic structure. So trust me, if you open these videos, you might have learned the topic in full. Let me show you stoichiometry. So stoichiometry, we have all the way up to 21 videos, including the story sheet solutions, which will help you to practice both the concepts and also prepare for questions. Okay, so feel free to head over to the site and check out these videos on your own. So equally, biology videos are also available, which you can also basically get to access. So these are the topics available so far. Yeah, so pretty much these are the ways you can easily access our full membership videos that you don't have access to on the channel.